Hello, and welcome back to the course on classical electromagnetism. So we are still on the sixth chapter of this course. So before we proceed with this lesson, let us first review some concepts in the previous chapters or lessons. So in the previous lessons, we have discussed about motional EMF, and it's basically just a potential quantity. Uh, it's equivalent to the induced electric field that dl, or where the induced electric field is essentially equal to v cross v. So v is the speed of the motion. We also have related this to Faraday's law, the flux rule for motional EMF, that the EMF is also equal to the negative change of negative time rate change of magnetic flux. And in our previous chapters, we have discussed about the curl of an electrostatic field. So if you have an electrostatic field, it doesn't have a curl. So it doesn't curl. It actually has a uniform direction. So for this lesson, we will be discussing about or we will be focusing on induced electric fields caused by electromagnetic induction. So Faraday's law describes the changing describes the changing magnetic flux can induce an electric field, and this is the basic principle of electromagnetic induction. So you have learned the basics of electromagnetic induction in your basic electromagnetism course. So basically, we relate the motional EMF and the flux rule for motional EMF. So, and we get this equation. So this is basically the integral form of Faraday's law. Now, if we substitute the equation for flux, which is just B dot dA, we get this. And if we use Stokes' theorem, we get the differential form of Faraday's law, which describes the curl of an electrodynamic field. Take note, this is electrodynamic field. So the curl of an electrostatic field is 0. But if you now have an electrodynamic field, that field is actually caused by a changing magnetic flux, or in this case, a changing magnetic field. So for instance, our electrodynamic field here is now time dependent. So for example, you have a changing magnetic field along this SA conductor, and it's increasing. Its change in strength with respect to time, change in magnetic field with respect to time, is positive. So that will create an induced electric field in the opposite direction. Therefore, there will be an induced electric field in this direction. It will curl around the magnetic field. So take note, the direction of the electric field is or the curl of the electric field is in the direction of the negative change of magnetic field. So if the magnetic field is changing in this direction, then the curl is in this direction. But if the magnetic field is is in this direction, but it's decreasing, therefore its change is in this direction, therefore the electric field is in the opposite direction. So that is basically electromagnetic induction. You have learned most of that in your basic physics. So the direction is always in the opposite of the change. So this is what this means. Negative means opposite, and derivative means change, opposite of the change. So similarly, if you have a changing electric field, conversely, you will also have a changing magnetic field that is curling around your changing electric field. So that is basically electromagnetic induction. Okay. For this first example, we have a loop in a solenoid. So we have a solenoid. This is our solenoid. And this solenoid is actually carrying an alternating current, meaning the electric field inside the solenoid is also alternating. So I just put the direction of the magnetic field in this direction, but it could actually be in the opposite direction, because our magnetic field, since our current is alternating, our magnetic field will also be alternating along the z-hat axis. So it will be At one point, it will be along the positive z-axis. At another point, or at another time, it will be on the negative z-axis. So it's oscillating along the z-axis. So we place a circular loop with radius b over 2 inside the solenoid of radius b. So the magnetic field inside the solenoid is oscillating along the z-axis. Find the induced electric field on the loop as a function of time. Okay, so in order to solve this, we must first find what is the magnetic flux. So the flux on the loop. So the flux on the loop, magnetic flux, is integral of b dot dA. B dot dA. Now, since the magnetic field is only time dependent, therefore at every point in the area of the loop, the magnetic field value at a certain time will be the same. It will be uniform at all points in the area of the loop. Take note, it's only in the area of the loop. So we can take it out of the integral. So you will just have b that integral dA. Integral dA is just the total area of the loop. So it will just reduce to b that the total area, b dot a. So our magnetic field is given b naught cosine omega t z hat. We dot it with the area of the loop, the area vector. So the area vector is just the area of the loop. In this case, it's a circle, so it's pi radius squared, so pi b over 2 squared. And this direction is in the same direction as the magnetic field, so z hat. So from here, we see that the flux is just equal to pi b squared b naught cosine omega t over 4. So knowing the flux, we can now solve for the induced EMF and the induced electric field. So the induced EMF is just a negative change in the flux with respect to time. So basically, just take the derivative of this with respect to time and then negate it. And this is also equal to the closed integral of E dot dl. So dl here, our dl, if we go back to our loop, our dl is in the phi direction. So our dl, if we take a dl with differential length, take note, the differential length is along our loop. Say this is our differential length. I'd say it's in that direction. It's a curling around, or it's moving around the loop. So this is our dl, and our electric field is actually also in the same direction. This is our electric field. So our electric field and dl are both in the phi hat direction. So therefore, E dot dl is just E dl because they have the same direction, phi hat. Okay. And since the electric field at all points within the loop is just the same, therefore I can take it out of the integral and I will just get E times the total, the closed integral of dl is just the total length of the loop. So this is just equal to E times the total length of the loop. In this case, the total length of the loop, if your loop is a circle, then it's 2 pi circumference, 2 pi times the radius. So you have 2 pi times the radius, which is b over 2. So you have pi b, so the 2 will cancel out. So for the derivative of this, we get the time derivative of that. So the only time component is cosine omega t. Derivative of cosine is negative sine omega t times omega. And you have the negative sign, so you get a positive result. So you will get pi b squared omega b naught sine omega t over 4. And this is equal to E times pi b. Solve for E, and you will get E is equal to omega b naught sine omega t over 4, and its direction is actually phi hat. Actually, it will also oscillate. It will alternate, meaning at one point its direction is a counterclockwise. At another point its direction will be clockwise. because sine omega t can have a positive and negative values, meaning it's the direction of this electric field is phi hat and negative phi hat. Half of the time it's phi hat, half of the time it's negative phi hat. So by the way, I forgot to emphasize that this electric field is time dependent. It's an electrodynamic field. Okay. So this is our result for the electric field. So another example. So we have a uniform magnetic field pointing straight up. It fills a circular region of space. If the magnetic field is changing in the wire, what is the induced electric field? So I highlighted here the word uniform to signify that it's uniform with respect to position, with respect to space, but it's not uniform, it's not constant with respect to time. So the uniform magnetic field here only means that at all areas of this circular region here, the magnetic field value at every point in this circular region of space here are the same. The magnetic field values are the same. But the magnetic field values are changing with time, but they are not changing with space. Okay. So if the magnetic field is changing in the wire, what is the induced electric field? Sorry, if the magnetic field is changing with time, what is the induced electric field in this circular regions of space here? Okay, so basically this is just a sheet, and as you recall, when you discuss about the electric field of a sheet of charge, you actually start with a circle and then make the radius greater, or increase the radius until it becomes an infinite sheet of charge. So there's actually no loop here, but we are trying to find the electric field in the region perpendicular to the magnetic field. Okay. So we use again Faraday's law. Use the integral form. Closed integral of E dot dl is equal to the negative time rate change in magnetic flux. Okay. So again, the electric field, so we make an Amperian loop, and along our Amperian loop we get some differential length. So this is our dl, and our dl in this case is in the same direction as the electric field. So again, if this is the direction of the magnetic field upward, then the electric field in this case will actually curl around the magnetic field. So that is their role, or yeah, that's the role between magnetic field and electric field. They're curling around each other. Okay. So also in our Amperian loop, at all points in our Amperian loop, the value, or the value of the electric field are the same at all points in the Amperian loop. So meaning I can take it out of the integral and I will be left with integral of dl. So basically integral of dl, total integral of dl is just the total length dl. In this case, it's the circumference of the loop. So our loop has a radius s. So basically, this integral will become E times 2 pi s. And then the flux is just magnetic field times the area. So we will assume that the area of the loop is in the same direction as the magnetic field. So in that case, take note, magnetic flux is just integral of b dot dA, not closed integral, it's the integral b dot dA. So the magnetic field again is uniform at all points in the loop, in the area of the loop. So I can take it out of the integral, and I will be left with b dot, the total area, b dot a. So b, the magnetic field and the area vector are actually pointing in the same direction, so it will just be reduced to b times a. So basically this is the derivative of b times a. But our area of the loop here is not changing, only the magnetic field. Therefore, I can take out the area. So the area of our loop here, circle, is pi r squared, or in this case, pi s squared. I take out the area of the differentiation, and I'm left with dB dt. So that one. So therefore, the electric field magnitude or value is s over 2 dB dt, and its direction actually is, if assuming this is the positive z direction, then this direction curling around the z is the phi hat direction. Okay, so this is our result. So the electric field depends on the change in magnetic field, dB dt. So this is our result. So if B is increasing, meaning dB dt is positive, because B is increasing. That means that the direction of the electric field is clockwise, in the opposite direction, so negative phi hat. But in the event that B is decreasing, so dB dt is negative, there's a negative sign here, so you will have a positive phi hat direction. So meaning, in the event that B is decreasing, then the induced magnetic field will be in this direction, and the induced electric field will be counterclockwise. So again, in electromagnetic induction, all you need to think about is that nature doesn't like changes in flux. So if you increase the magnetic field, nature will always counteract to decrease it, to equilibrate it, to balance it, to get rid of the change or the increase. So that's always the reaction of nature. Okay. For our last example, we have an infinitely long straight current carrying wire, and it carries a slowly varying current. So I will just discuss the significance of what's a slowly varying current, maybe in the next chapters. It actually has something to do with the displacement current, which we'll still be discussing in the next lessons. So you are then asked to determine the induced electric field as a function of the perpendicular distance s from the wire. So we know that if you have a current carrying wire I, the magnetic field at distance s from this wire is given by this equation, mu naught I over 2 pi s. So since our board is only two-dimensional, so we can only draw the magnetic field as in the upper region it's out of the page, and in the lower region of the wire it's into the page. So it's curling around the current. So meaning the electric field is actually in this direction. So in all the regions, the electric field is in this direction. Okay. So we are then asked for the induced electric field. So what is the induced electric field now? So we know that the direction of the induced electric field is in this direction. So let's assume that this direction is the z-axis, and this direction, based on our definition of a magnetic field, this is the phi hat. The curl is the phi hat direction, and therefore this is the z direction, or the z hat direction. So our electric field is in the z hat direction. So we make an Amperian loop, because in our formula of E dot dl, dl is an Amperian loop. So from our equation, from Faraday's law, we have E dot dl is equal to negative change in flux respect to time. So dl here is this one. So it always, the Amperian loop always encloses the current, encloses the magnetic field lines in this case. Okay. So this Amperian loop encloses magnetic field lines. Okay. So this is our DL now. You will notice that our DL, our Amperian loop, has four sides. So this is our DL1, that's that direction. This is our DL2, it's in that direction. This is our DL3, it's in that direction. and this is our DL4. See, it's not direction, so it's looping. So if you take E dot DL, close integral of E dot DL means close integral, so all over the loop. Now this is that product E dot DL, meaning DL2, this side of the loop and this side of the loop doesn't have a contribution because E is perpendicular to DL2 and DL4. Therefore, E dot DL is 0 because they're 90 degrees. Their angle is 90 degrees. So only DL1 and DL3 will have a contribution. Now for DL1 and DL3, the electric field along the line DL1 is just the same. It's the electric field at a distance S0. And the electric field at DL3 or the line 3 are also the same. It's the value of the electric field at a distance S from the wire. So meaning E is constant. It doesn't depend on the length. You can take it out of the integral, so you will just have E times L. But for two lengths, so so you will have E, say L1, and then E close integral of, I will put it like this: electric field at S0, and this is DL1, plus E at S close integral of DL3. So that one. Sorry, I already removed the dot product, so E dot DL1 is just E DL1. But E dot DL3 is in the negative z-axis, E is along the positive z-axis. So the direction is, or the angle between them is 180 degrees. So that will make a negative E dot DL. So negative E electric field at S DL3. So of course these lengths, the total length is just, let's assume that this length is just L. So the total length of DL3 is just L. The total length of DL1 is just also L. So I'm just gonna use small L. Okay. So going back to our integral. So our flux here is actually just integral of B dot dA. Basically, you will get integral of B, which is this one. So mu naught I over 2 pi S phi hat. And we will assume that our dA is also in the phi hat direction. So we will assume that our dA, differential area, is in the phi hat direction. So the area of this loop is also in the phi hat direction. So take note that this can be in any view. So this loop is not only in this plane specifically. This is actually in the what plane is this? SZ plane. So SZ plane. So that's just not a single plane basically. So it's one of the SZ planes. So you dot it with dA. In our case, the area of our loop is, it has a length L, and its width is dl. In this case, dl is, since this is the S direction, then ds. So you have L ds phi hat. So this is our dA. This is our magnetic field. This is our dA. So you will get basically mu naught I, I'll just use small l, L over 2 pi integral of ds over s. Integral of ds over s. Okay. So this is basically ln of s. So ds over s. So you will get s. It starts from s naught the distance of this side, and then to S naught to S. Basically, your flux will become, so you have negative d dt of the flux, which is mu naught I L over 2 pi ln of, this is S naught to S, S naught to S. So ln of S over S naught. So of course, the only thing that is changing with time in this equation is the current, because this is a slowly varying current. So the di dt, and you will get, so this now becomes electric field at S naught. Then you have the same L, so minus electric field at S multiplied by L, and then you will have this is basically the ln of S over S naught is basically ln of S minus ln of S naught. So I will get, I'm gonna write this one first, negative, negative, you get positive. So I will get mu naught L over 2 pi ln of S naught di dt minus mu naught L over 2 pi ln of S di dt. That one. So divide both sides by L, and you can now solve for E of S. So from here you can make a comparison, and you will get a value of mu naught over 2 pi di dt ln of S. That is the electric field as a function of S. And take note here that our current is time dependent. It depends on time. So see here is just some constant with respect to S, but it can actually depend on T in this case. But it is see here is a constant with respect to S. Some integration constant. And that is it. That is the end of this lesson. So for the next lesson, we will be still talking about electromagnetic induction, and specifically we will talk about inductors and inductance. So I will see you again in the next lesson.